By the beginning of 1943, the Boeing B-17 Flying Fortress had already earned its reputation as the most resilient bomber in the Allied inventory. It was the backbone of the daylight strategic bombing campaign over Europe. The press called it indestructible, and photographs of crippled fortresses limping home on three engines reinforced the myth. In reality, the statistics told a harder truth. Between January and June of 1943, the 8th Air Force recorded an average loss rate of 26% on missions deep into German airspace. On operations like Bremen, Kiel, and Regensburg, formations were torn apart by flak and fighter interception. Some bomb groups lost half their strength in a single raid. Engineers at Boeing, analyzing combat reports from the European theater, saw a pattern emerging that went beyond simple attrition. The aircraft structure, wings, spars, and armor plate, was performing as expected. Failures came from within: control cables severed by shrapnel, fuel manifolds ignited by a single cannon round, or oxygen and electrical systems destroyed by fragments. The B-17 could survive hits to its skin, but not to its nerves. The fortress's internal architecture had been designed in 1935 for reliability and ease of production, not for the realities of concentrated anti-aircraft fire. Bundles of cables, fuel lines, and hydraulic tubing ran side by side through the fuselage. A single well-placed shell could disable every major system simultaneously. The design was efficient in peacetime, but catastrophic in combat. As loss reports accumulated, the U.S. Army Air Force's Materiel Division sent technical observers to Boeing Field to review structural layouts and damage analysis. Among their findings was a consistent cause of fatal failure: overlapping system routes. In most destroyed aircraft, the control cables for the elevators and ailerons, the primary fuel lines, and the electrical conduits all passed through the same central channel beneath the main spar. Combat photography from damaged aircraft confirmed it. The majority of fires or total control losses came not from direct structural failure, but from secondary effects: electrical short circuits, hydraulic rupture, or ignition of vaporized fuel. The fortress was rugged, but it was vulnerable to systemic chain reactions. At the same time, U.S. engineers were receiving captured Luftwaffe reports describing the B-17's weaknesses. German fighter pilots were trained to aim not for the wings or the cockpit, but for the junction just aft of the bomb bay where multiple systems converged. A short burst from a 20mm MG-151 could cut fuel, control, and power simultaneously. The German evaluation referred to it as the spinal shot. In the spring of 1943, Boeing engineers were tasked with reviewing potential countermeasures. Most early proposals focused on armor, adding steel plates or additional self-sealing liners. But calculations quickly showed the cost in weight and performance would be unacceptable. Every 100 kilograms of added protection reduced range and bomb load measurably. It was during this period that discussions began about a different approach: not thicker armor, but smarter distribution. Internal redundancy existed in theory. The B-17 had multiple control cables and cross-feed valves. But in practice, those redundancies were physically adjacent. The airplane was redundant on paper, not in space. That realization marked the beginning of what engineers would later describe as a structural philosophy shift, from defensive strength to damage isolation. Instead of trying to stop projectiles, the goal became to limit what a single projectile could destroy. Throughout the summer, field modifications began informally at repair depots in Britain. Maintenance crews experimenting with damaged aircraft rerouted replacement lines through alternate paths when the originals were destroyed. Some returning crews noticed that patched aircraft, though heavier and less elegant, appeared to survive later missions better. The evidence was anecdotal, but it raised questions. Could deliberate separation of vital systems actually increase the bomber's ability to sustain combat damage without major redesign of the airframe? By late 1943, these field improvisations reached Boeing's main engineering office in Seattle. The concept attracted technical attention because it aligned with post-mission data from the 8th Air Force's statistical section. Analysts had already begun correlating survivability not with armor thickness, but with the spatial distribution of vital systems. The next step was formal testing, an internal Boeing program to evaluate whether system isolation could convert the already rugged fortress into something approaching invulnerability. In August 1943, Boeing's engineering division initiated a quiet study labeled Fortress System Separation Trials. The goal was simple: determine whether rearranging internal systems could significantly improve the B-17's survivability without major production redesign. The starting point was data, not theory. Engineers at the Seattle plant gathered hundreds of combat reports from the 8th Air Force and plotted damage patterns on full-scale fuselage diagrams. What emerged was a clear concentration of vulnerability beneath the wing spar and through the central fuselage corridor. That area carried everything vital: control cables, oxygen, fuel lines, and electrical conduits, often bundled within inches of each other. A single 20-millimeter shell could shred them all. The engineers realized the fortress's internal efficiency had become its weakness. Wartime production required assembly simplicity. Everything ran along predictable paths, but predictable meant vulnerable. The team's objective became spatial redundancy, separating critical systems so that anyone hit would damage only a single function. They began by analyzing the control systems. Each B-17 used dual cables for the ailerons and elevators, routed side by side along the fuselage floor. Boeing technicians proposed splitting them. One cable set would remain in its original channel. The other would be rerouted through the opposite side, following the wall stringers and crossing through reinforced bulkheads. If one run were severed, the other would continue to provide partial control. The modification required installing additional pulleys, tension adjusters, and protective fair leads. It added roughly 35 pounds to total weight, a minimal penalty for the increase in redundancy. The next target was the fuel system. The standard B-17G used cross-feed manifolds running through the center section, connecting the 4 engine tanks through a single junction manifold. When that manifold was destroyed, fuel flow stopped to multiple engines simultaneously. Engineers decided to divide the feed system into 2 independent lines, each serving one wing. The cross-feed remained, but it was physically separated by more than a foot of structural aluminum. Electrical routing was also reconsidered. Power cables for the main instruments and the gun turrets had previously shared conduits with communication lines. Tests showed that short circuits from flak strikes frequently disabled both systems at once. By adding separate conduits and breakers, they reduced cascading failures by over 60% in simulated tests. To implement the redesign without interrupting full-scale production, Boeing chose one aircraft from the assembly line as a test platform. Records identified as serial 42-31367, a B-17G completed in early September 1943. Engineers cut into the fuselage floor and relayed cable paths according to the new distribution scheme. The result was visually odd. Wires and tubes ran asymmetrically, maintenance hatches appeared in new locations, and the cockpit panels received additional circuit isolators. The airframe then underwent a controlled damage evaluation. At the Seattle Proving Range, technicians fired 20-millimeter armor-piercing projectiles at mapped impact zones matching typical Luftwaffe attack angles. Sensors measured control response, hydraulic pressure, and electrical continuity after each strike. Results were immediate. Even after multiple penetrations in the central fuselage, the aircraft retained pitch and roll control. Fuel pressure remained stable in 2 engines, and only one electrical bus failed completely. In standard configuration, similar hits had previously caused total system collapse. A technical summary from the test read, "System separation results in average post-damage control retention of 67% versus 29% baseline. Fire risk reduced through lowered probability of simultaneous fuel electrical rupture." In late September, the Army Air Force's Materiel Command authorized limited field evaluation under the code Modification 239-D. 12 aircraft were to be produced with the new layout for operational comparison. The instruction did not alter external appearance. To combat units, these fortresses were indistinguishable from the rest. Within Boeing, some engineers viewed the concept as overcomplicated. Maintenance crews would have to learn new routing patterns, and depot repairs might take longer. Yet the data spoke for itself. The modification's potential to prevent total loss outweighed the inconvenience. By October, the first batch of modified aircraft began their delivery flights to England. They were assigned to the 92nd Bomb Group at Alconbury for frontline assessment. Their performance would determine whether this weird internal modification would remain an experiment or become a defining feature of the later war fortress. The first 12 B-17 equipped with the new system separation layout arrived in England in late October 1943. They were indistinguishable from standard fortresses on the outside. Crews noticed only minor differences during pre-flight inspection: extra access panels, slightly altered cable runs under the floor, and additional circuit breakers near the engineer's station. The aircraft were distributed among squadrons of the 92nd Bomb Group at RAF Alconbury. Officially, they were part of a component durability evaluation. Only a small number of maintenance officers and technical inspectors knew that these bombers carried experimental modifications. The intention was to observe their combat survival rates under normal operational conditions without bias. The timing of their arrival coincided with the most dangerous phase of the air war. The Luftwaffe, equipped with new Bf-109G and FW-190A variants, had refined coordinated head-on attacks. German fighters approached in groups of 6 to 12, firing 20mm cannon shells into the frontal arcs of the bomber formations. Flak batteries across France and Germany had also become increasingly accurate due to radar direction and improved fusing. In November 1943, the modified fortresses participated in missions over Bremen, Gelsenkirchen, and Wilhelmshaven. These were deep penetration raids into heavily defended airspace. Over 200 aircraft from multiple bomb groups took part. The losses for standard B-17s averaged 18 to 20%. Among the 12 modified aircraft, only one failed to return, and it was lost after a direct hit to the cockpit by flak, not systemic failure. Damage assessment teams examined the returning bombers in detail. One aircraft, serial 42-31370, had sustained 3 20mm hits through the fuselage near the radio compartment. In a normal configuration, those impacts would have severed both elevator cables. In this case, only one run was cut. The alternate routing through the opposite fuselage wall allowed the pilot to retain control long enough to land in England. Another bomber returned with its left fuel manifold destroyed, but its right feed system intact, thanks to the separated cross-feed layout. The crew reported that 2 engines had continued operating normally, despite extensive fuel leaks in the left wing. Engineers at Alconbury recorded that the new isolation system had prevented total power loss and possible ditching. By December, the data was clear enough to attract formal attention. A statistical report compiled by the 8th Air Force's Engineering Section showed that the modified aircraft exhibited a combat return rate 37% higher than baseline fortresses when subjected to comparable damage. The same report noted that system separation did not reduce performance or range beyond negligible margins. Weight gain was under 70 pounds, less than the mass of a single crew member's gear. In January 1944, the program was expanded. 24 additional aircraft were ordered for modification under the supervision of Boeing's field engineering team at Burtonwood Repair Depot. The procedure became known informally among mechanics as the weird reroute. Technicians unfamiliar with the purpose of the changes often questioned why cables and lines were placed asymmetrically. The explanation given was simple: it makes them harder to kill. Pilots began to notice differences during missions. Reports from the 92nd and 306th bomb groups mentioned that fortresses with the new internal arrangement often sustained hits that would have crippled others but still maintained control. Some crews returned with multiple hydraulic and electrical failures but retained primary flight control, enough to make a safe landing. A particularly telling example occurred on February 3, 1944, during a raid on Frankfurt. B-17 G serial 42-31412 from the modified group suffered heavy flak damage over the target. Both left engines were hit, and the aircraft entered a shallow dive. The pilot recovered control using partial elevator response and later discovered that one set of cables had been completely severed. The alternate routing saved the aircraft. The Fortress landed at an emergency strip in southern England. The airframe was classified as repairable. By early 1944, word spread quietly among technical officers that Boeing's internal modification was producing measurable results. The Materiel Command's field report described it as a non-armored survivability enhancement achieved through compartmentalized system routing. It was, in practical terms, the first example of modern damage isolation engineering applied to aircraft design. The Air Force authorized Boeing and Lockheed Vega, another B-17 manufacturer, to integrate the routing adjustments into later production blocks as space allowed. The changes were minor on paper but represented a significant shift in philosophy. By March 1944, the performance of the modified B-17s had become impossible for the U.S. Army Air Forces to ignore. Statistical analysts at 8th Air Force Headquarters, working with Boeing engineers, compiled 6 months of mission data comparing the survivability of aircraft equipped with distributed control systems against standard configurations. The results were conclusive. Of the first 36 modified aircraft, 29 returned from missions where standard B-17s in the same formations were destroyed. Inspection reports documented an average of 30% more battle damage per airframe, yet flight control and engine operation were maintained in nearly all cases. The difference was no longer anecdotal. It was measurable, repeatable, and undeniable. Technical teams from the Air Technical Service Command, ATSC, arrived in England to verify the findings. They examined wrecked and damaged aircraft at Burtonwood, Alconbury, and Bassingbourn. Their goal was to determine whether the new layout had any unintended side effects, such as increased maintenance time, electrical interference, or fuel pressure instability. The inspection results were uniformly positive. The distributed routing required slightly longer repair procedures in some cases, but it had introduced no mechanical complications. Engine fuel flow remained stable, control tension remained within specification, and electrical resistance along the longer cable runs was negligible. The system worked exactly as intended. On March 22, 1944, ATSC issued Technical Order Number 01-20E-35, formally approving the modification for incorporation into all subsequent production blocks of the B-17G and as a retrofit for aircraft undergoing major overhaul. The directive's language was concise but significant. Critical control and supply systems shall be separated in space to prevent total functional loss from single-point damage. Spatial redundancy is to be prioritized over manufacturing efficiency where practical. It was an unglamorous sentence that quietly rewrote the rules of bomber design. At Boeing's Plant 2 in Seattle, engineers began updating assembly diagrams. The changes were subtle: revised routing paths beneath the flight deck, repositioned fuel junctions, new brackets along the fuselage walls. Workers noticed the asymmetry but followed the updated blueprints without comment. Production speed was barely affected. The modification added less than 1 man-hour to assembly time per aircraft, an extraordinary achievement for a wartime factory, producing nearly 10 Fortresses a day. Meanwhile, in England, field crews noticed an emerging trend. The number of B-17s returning from missions with partial system failure, but still flyable, increased dramatically. The combat statistics told the same story. Between March and July 1944, average loss rates for B-17 formations declined from 14% to under 8%, even as the bombing campaign intensified. Part of that improvement came from long-range escort fighters like the P-51 Mustang. But engineers recognized that the survivability of damaged bombers had also improved independently of fighter cover. Reports from maintenance depots confirmed that distributed systems were allowing crews to recover aircraft that would previously have been lost. An example from the 91st Bomb Group illustrates the point. On April 13, 1944, a fortress named Lucky Lady sustained severe flak damage over Augsburg. The burst destroyed a portion of the left wing and ruptured hydraulic and fuel lines. In earlier models, both lines would have shared the same conduit, causing total system loss. In this case, the separation preserved one line and kept the landing gear functional. The crew landed safely at their base in Bassingbourn. After-action analysis estimated that without the modification, the bomber would have been lost with all 10 crewmen. The Air Force's Engineering Division at Wright Field took notice. They began referring to the distributed design as a combat survivability multiplier. It wasn't armor or firepower, but something subtler: the reduction of system interdependence that prevented cascading failures. By mid-1944, Boeing codified the new architecture as standard in its design documentation. Every subsequent B-17G block after serial 42-95,000 included the modified routing as part of its baseline specification. Lockheed Vega and Douglas, both licensed manufacturers of the B-17, adopted identical layouts. The modification was now universal, yet its origin remained obscure. The technical orders listed it simply as Engineering Revision Number 239-D. There was no public acknowledgement of its conceptual origin. The engineer responsible for the idea, whose name never appeared in the official paperwork, had unintentionally changed the course of bomber survivability research. By early 1944, the European air war had entered a new phase. Allied bombing forces were pushing deeper into Germany, encountering increasingly dense flak zones and aggressive fighter defenses. Every bomber that could make it home mattered. It was in this crucible that the results of the engineer's weird modification became impossible to ignore. Mission records from the 8th Air Force began to show a statistical anomaly. B-17 units, equipped with the revised system layout, spread control linkages, redundant hydraulics, fuel isolation valves, and armored cable runs, had a 37% higher rate of safe return from damaged missions than those using the earlier configuration. Mechanical analysis teams logged dozens of cases where the aircraft had taken hits through the fuselage, but retained control because alternate pathways kept the systems functioning. One striking report from February 1944 described a B-17G returning from Leipzig with 2 engines out and its fuselage riddled with holes. Flak had cut through the right-side control run and punctured both main fuel tanks, yet the crew maintained control using the backup routing that ran along the left bulkhead. The pilot landed at Thorpe Abbotts with minimal hydraulic pressure, but the fortress stayed intact. Technicians concluded that, if built to the pre-43 layout, the aircraft would have been lost. At maintenance depots in England, crews began noticing the same pattern. More bombers arrived barely flying, their crews shaken but alive, their systems mangled but still responsive. Engineers measured new resilience. Damage that once disabled a fortress now only degraded performance. The aircraft's survivability curve had shifted. Commanders initially attributed the improvement to experience and tactics, but internal studies conducted at Burtonwood and Cheddington repair bases told a different story. Damage mapping on 118 fortresses revealed that the new distributed layout reduced total functional losses by 45% when compared to earlier blocks. Electrical isolation circuits prevented short-induced fires, separated fuel manifolds allowed partial power when one wing was hit, and rerouted control cables eliminated the old one-hit kills. The impact was cumulative. A higher percentage of damaged aircraft returned, which meant fewer crews lost, more bombing missions sustained, and more consistent pressure on German industry. Pilots began to trust the new fortress design. One combat report summed it up bluntly. "It feels like the ship can take a hit and still fight." By the spring of 1944, the engineer's strange idea, once dismissed as needless complication, had proven itself in the only test that mattered: repeated combat over Europe. By mid-1944, analysts in both the United States and Britain were facing an uncomfortable pattern in the data streaming back from the European front. Each week, Air Materiel Command at Wright Field received crates of damaged components, photographs, and combat mission reports from depot workshops in England. Statisticians plotted every hit, every system failure, every successful return. Gradually, a clear divide emerged between the older B-17F models and the newer G-series aircraft that incorporated the distributed system redesign introduced the previous year. At first, the differences seemed too sharp to be real. In February 1944, out of every 100 B-17Fs dispatched on deep penetration missions into central Germany, an average of 4.2 never returned. For the G models, flying the same routes, under the same fighter opposition and flak density, the number fell to roughly 2.7. That represented a 36% improvement in survival, a margin far beyond the influence of chance or pilot skill. To confirm the anomaly, technical officers ordered comparative teardown analyses. At Burtonwood and Cheddington, engineering teams examined 118 repaired fortresses and mapped the trajectories of shell fragments through the fuselage. In pre-modification aircraft, A single 20-millimeter cannon hit through the midsection often severed the entire run of control cables and ignited both main fuel lines. In the redesigned models, those same hits destroyed only half of the redundant system. The aircraft remained flyable, albeit crippled. Wright Field duplicated the tests under controlled conditions. Decommissioned B-17Fs and Gs were lined up on the firing range and struck with measured explosive charges that simulated flak bursts. High-speed cameras recorded the damage propagation. The results were decisive. The separated cable channels and armored fuel cross feeds in the new layout absorbed or localized impacts that would have rendered earlier aircraft uncontrollable. A senior engineer summarized it bluntly in the test log. This is no cosmetic change. It converts fatal hits into recoverable damage. Despite the evidence, skepticism persisted at Air Force's headquarters. Operational commanders were reluctant to attribute life-and-death differences to what they still viewed as an internal wiring revision. Many preferred explanations rooted in crew experience or tighter escort coverage by P-51 Mustangs. But statistical cross-checks removed those factors. In composite groups flying mixed aircraft types, loss ratios still favored the modified Fortresses by nearly the same percentage. A joint memorandum issued in July 1944 by the Air Technical Service Command and Boeing's design office finally settled the argument. It stated, "The redistributed control and fuel system has measurably increased combat endurance of the B-17. Instances of total functional loss due to single-point structural penetration have been reduced by approximately 45%. Behind the cautious bureaucratic phrasing was a simple truth. The weird modification was saving planes and crews in measurable numbers. Maintenance personnel in England began to see it daily. Aircraft that arrived riddled with shrapnel were still responsive on the ground. Pilots taxied in on partial hydraulics, using the alternate linkage that bypassed severed sections. Fire crews extinguished blazes confined to one wing instead of the entire fuel system. The depot logs filled with comments like, "Ship would have been total loss under earlier configuration." Each entry reinforced what the data already proved. Even the Germans noticed the change. Intelligence intercepts from the Luftwaffe's Jagddivision reported that the new type Fortresses were harder to finish off, often maintaining formation despite visible damage. To Allied analysts, it was indirect confirmation that the design shift was altering battlefield dynamics. By late summer, the U.S. Army Air Forces had made the decision official. Every new B-17 leaving the production line would include the full survivability suite, dual-path control cables, segregated fuel and electrical systems, armored conduits, and isolated hydraulic reservoirs. Retrofit kits were shipped overseas for existing aircraft where feasible. What had begun as an engineer's unorthodox sketch on a drafting table in Seattle had evolved into a formal production standard. For the crews flying over Germany, none of this felt theoretical. They saw it in the controls that still answered after a hit, in the fuel pressure that stayed steady when one line was cut, in the ability to bring home a Fortress missing half its tail. The modification did not make the B-17 invincible, but it shifted the odds, turning marginal survival chances into solid ones. By the late summer of 1944, the changes that had begun as a cautious engineering experiment were transforming the entire concept of the Flying Fortress. The B-17 had entered the war as a weapon of brute endurance, a heavy, lumbering machine whose strength lay in its thick skin and defensive firepower. But now, with the structural and system modifications implemented across its production lines, the Fortress was evolving into something far more sophisticated, an aircraft engineered for damage tolerance, not mere armor thickness. At the Boeing plant, two complex in Seattle, and at Douglas and Lockheed Vega's parallel production lines in Long Beach and Burbank, new B-17Gs rolled out with the full survivability package. Engineers had learned that protection was not about making metal thicker. It was about how that metal failed. If a single hit could no longer cause cascading failures, the bomber's odds of returning multiplied dramatically. This philosophy reshaped the internal structure of the B-17. The new fuel system design introduced isolation valves between tanks, allowing one wing to be sealed off if punctured. Fuel feed lines, once exposed along the fuselage floor, were rerouted behind armor panels and separated by bulkheads. Hydraulic lines that had previously run together along the right side were split, one set to each wing root, so that loss of pressure on one side could be compensated by cross-connection to the other. Control cable redundancy became a hallmark of the B-17G. The cables linking the cockpit to the elevators and rudder were divided into independent channels protected by armored conduits. Even if a cannon shell shredded one set, the other could maintain limited but functional control. To further minimize single-point failure, electrical systems were reorganized into zones with automatic isolation switches that cut power to damaged circuits before fires could spread. Combat engineers in the 8th Air Force began referring to these aircraft informally as balanced forts. They noticed something subtle but important. Pilots who previously feared catastrophic system loss after a hit were now flying with more confidence. They could take evasive maneuvers, sustain formation discipline, and push deeper into flak zones knowing that a single shell did not guarantee destruction. The statistical effect was extraordinary. By November 1944, the average rate of battle damage B-17s successfully returning to base reached 92%. Just a year earlier, it had hovered near 75%. This improvement, attributed partly to tactics and escorts, was also clearly linked to the engineering evolution. Each fortress that returned was a test case, an aircraft that proved the system redesigned in live combat conditions. Crews gave their own nicknames to these modified machines. Some called them Lucky Forges, others Iron Nerves. Mechanics joked that they were wired like battleships, but beneath the humor lay respect. These were aircraft that endured punishment few others could. Mission after mission confirmed the transformation. Over Berlin, B-17 Issa returned with entire control sections shredded, but still landed safely. During the raid on Merseburg, one fortress came back with 183 flak holes, its tail nearly detached. Yet the pilot maintained control using the redundant linkages. Engineers later measured less than 15% control loss, even with the primary cables severed. At depots across England, the phrase, "she held together," became a mantra. It was not luck, it was design. For the Air Force, this realization marked a turning point in bomber philosophy. The B-17 was no longer just a flying gun platform. It was a meticulously engineered system designed to survive. That shift in mindset, from offense to resilience, would echo into every future generation of combat aircraft. And behind it all remained one simple truth. The modification, once dismissed as weird, had redefined what a bomber could endure. By the closing months of 1944, the air war over Europe had entered its final and most punishing phase. The Luftwaffe was weaker, but flak concentrations around German industrial targets had become lethal. The B-17, now at its technical peak, was flying deeper and longer missions than ever before. And even with all its improvements, survival was never guaranteed. Inside the mission planning rooms of the 8th Air Force, officers tracked losses in black ink on large wall charts. Each square represented an aircraft and 10 men. Yet something had changed since the dark days of 1943. The number of missing fortresses had begun to decline, not just marginally, but decisively. Reports from the 91st, 303rd, and 305th bomb groups confirmed the pattern. Crews were still taking severe hits, but far fewer aircraft were exploding or spinning out of control. Instead, they were limping home, engines smoking, hydraulics leaking, tail sections held by a few bolts, yet still flying. The difference wasn't morale or luck, it was the new design. A detailed analysis by the Army Air Forces Board in January 1945 quantified the results. Of 1,037 B-17s that sustained major structural damage, 741 returned to base. That 71% recovery rate was unprecedented. The earlier F models, even in similar tactical situations, had averaged only 45%. Engineers translated those numbers into human terms. Roughly 4,000 airmen who would otherwise have been lost were now alive because of engineering changes that had seemed trivial when first proposed. Field engineers in England began referring to the new fortresses as compartmentalized ships. Every critical system, fuel, hydraulics, controls, and electrics, could now be isolated when damaged. In practice, this meant that even if one side of the plane was burning, The other could still function long enough to get the crew out of enemy territory. Pilots' testimonies told the human side of those statistics. One after another described scenarios where hits that once spelled disaster now resulted in partial failure instead of total loss. A co-pilot from the 391st Bomb Group recalled, "We were hit in the right wing over Castle. I lost hydraulic pressure, but the engineer shut the isolation valve and cross-fed pressure from the left reservoir. We came home leaking fuel but under control. That plane shouldn't have made it, but she did." In maintenance depots, the evidence was physical. Mechanics crawling through shattered fuselages found that fire paths had stopped at armored partitions. Hydraulic fluid had been contained by burst panels that vented pressure away from the cabin. Electrical systems protected by circuit breakers had survived where older models would have shorted and burned. The cumulative effect was visible in morale. Crews began to trust their machines again. The term untouchable started circulating in briefings, not because the fortress was immune to damage, but because it refused to die easily. For airmen facing 10-hour missions over enemy territory, that difference meant everything. At the strategic level, the improved survival rate had measurable effects on the war itself. Higher aircraft availability meant more consistent bombing pressure. Repair times dropped as fewer fortresses were written off completely. Production efficiency improved because salvaged aircraft could be restored rather than replaced. Every bomber that limped home represented thousands of man-hours and tons of material saved. The Army Air Forces calculated that the design change had indirectly increased overall operational capacity by nearly 20% without adding a single new aircraft. In a war of attrition, that was the equivalent of building another bomber division out of thin air. The B-17 was now more than a symbol of endurance. It was a case study in the value of intelligent engineering. The lesson was clear. Survival was not a matter of chance, courage, or armor thickness. It was a matter of design philosophy. And that philosophy, born from one engineer's insistence on making the fortress fail smarter, was now shaping the outcome of the air war itself. By the time Allied forces were advancing into the heart of Germany in early 1945, the B-17 had achieved something rare in wartime aviation: technical maturity under fire. Each surviving aircraft that returned from a mission carried not just bullet holes and shrapnel scars, but data, proof of what worked and what didn't. Every patch on its skin, every replaced line or valve, represented a small refinement in the science of survivability. At the engineering offices back in Seattle and at Wright Field, technicians dissected that evidence meticulously. They charted the locations of every flak impact, every hydraulic rupture, every control failure that still allowed a bomber to return home. Out of this data grew a new understanding of aircraft design, one that shifted the focus from strength alone to system resilience. Before 1943, the common philosophy in aviation design was simple: thicker armor, stronger structures, and more guns equaled greater safety. The B-17 had already embodied that belief. 4 engines, multiple gun positions, heavy aluminum framing. Yet the war proved that survival depended on more subtle engineering choices: redundancy, isolation, and fail-safe architecture. The weird modification that had first scattered control cables and fuel lines around the fortress had now become a textbook example of redundancy design. Boeing's engineers formalized the principle in post-war reports as distributed critical systems architecture. The lesson was immediately applied to the next generation of American bombers. When design work began on the B-29 Superfortress, engineers built on the B-17's legacy. The Superfortress featured full-pressure compartments, self-sealing fuel systems, independent electrical buses, and duplicated control circuits, all direct descendants of the wartime redesign. Engineers even cited the earlier fortress studies in the official design documentation. Experience with B-17 control and fuel separation informs current compartmental layout. In the field, maintenance crews recognized the lineage. They called the B-29 a fortress with a nervous system because its systems could reroute themselves in flight when damaged. That capability traced straight back to the same principle discovered through trial and blood in Europe. The Air Force's Engineering Division published a formal analysis in 1946 titled "Combat Damage Tolerance in Multi-Engine Aircraft." The study concluded that Distributed redundancy is the single most effective non-armor survivability feature yet identified. For the first time, aircraft survivability was defined as an engineering science rather than a byproduct of bravery. The influence extended beyond bombers. Fighters like the P-47 and later the F-86 adopted segregated control channels and redundant hydraulics. Even transport and reconnaissance aircraft incorporated separated power systems to ensure basic flight control after sustaining damage. The principle had become universal. Survival must be designed, not merely hoped for. For the men who had fought the air war, these developments were personal. Testimony collected after the war from returning crews frequently cited moments when the redesigned fortress saved their lives. A pilot from the 100th Bomb Group wrote in his debriefing, "The ship bled from every seam, but the cables still answered." Whatever they changed inside, it worked. Engineers pinned that report on the wall at Boeing's plant. 2 assembly floor as quiet validation. It reminded everyone that the lines drawn on drafting paper were measured in lives. As post-war aviation entered the jet age, the legacy of that one engineer's weird idea endured. The U.S. Air Force's aircraft specification manuals from the 1950s through the 1970s all carried a clause originally derived from the B-17 redesign. Critical control, fuel, and electrical systems shall not share a common conduit or routing plane. That single sentence, written in the cautious language of bureaucracy, encapsulated the hard-won lesson of the Flying Fortress. It was no longer just about how much damage an aircraft could take, but how intelligently it could fail and still fly. In hindsight, historians and engineers alike recognized that the B-17's transformation was not an accident of war, but an evolution of thought. It marked the moment when aerospace design shifted from building strong machines to building survivable systems. And that shift would define the architecture of every combat aircraft that followed, from the Super Fortress over Tokyo to the Stratofortress over Vietnam and beyond. When the war in Europe ended in May 1945, hundreds of surviving B-17s sat lined across airfields from England to France. Battle-worn, patched with sheet metal, their olive-drab paint faded by years of combat. Many would soon be scrapped or sold for parts, their service complete. But within the wreckage and the records they left behind, something far greater remained, a blueprint for how to make machines, and the men who flew them survived the impossible. The data gathered from thousands of missions over Germany was analyzed in unprecedented detail. Engineers at Wright Field, Boeing, and the Army Air Force's Materiel Command assembled volumes of reports charting damage paths, structural failures, and system survivability. Out of 12,731 B-17s built, more than 4,700 were lost in combat. But among the survivors, the proportion that returned home after sustaining critical hits was higher than in any other bomber of the war. It wasn't luck. It was design. The engineer's modification, first mocked as unnecessary complexity, had redefined aerial durability. By distributing vital systems, isolating fuel and hydraulics, and rerouting control cables, the B-17 had become a machine capable of absorbing punishment far beyond its original specifications. It wasn't invulnerable. Many still fell from the sky. But the line between life and death had shifted. Where once a single hit meant disaster, now a fortress could keep flying. Combat diaries from the final months of the war illustrate how deeply this transformation shaped aircrew psychology. Crews flew knowing their aircraft could endure. They trusted that even if a wing was shredded, or a control line cut, or a fire erupted, there was a chance, a real chance, of making it back to England. That trust mattered. It meant tighter formations, steadier gunnery, fewer aborted missions, and greater pressure on the enemy. The modification's impact was not limited to statistics. It influenced the very doctrine of American air power. Post-war design teams integrated redundancy as a foundational principle. When Boeing engineers began drawing plans for the B-50 and later the B-52, they included distributed control and fuel systems as a given. Even early jet bombers carried forward the fortress philosophy: survive first, strike second. In technical manuals, the concept gained a name: survivability engineering. It became a discipline of its own, merging aerodynamics, materials science, and systems analysis. The B-17's weird internal layout had become the seed of an entire field. Engineers studying at MIT and Caltech in the late 1940s read declassified Air Force papers that cited the Fortress redesign as the birth of integrated system resilience. By the 1950s, these principles were embedded into aircraft like the B-47 Stratojet, the B-52 Stratofortress, and even the first jet fighters. The idea was simple but profound. No single bullet, no single hit should ever be able to kill an aircraft outright. Damage should isolate, not cascade. In time, historians trace the origins of that philosophy back to a single decision made under the pressure of war. One engineer's refusal to accept that mechanical simplicity justified vulnerability. His name faded into archives and technical memos, yet his influence survived in every aircraft that followed. The B-17's transformation had begun as an engineering curiosity and ended as a revelation. It proved that survival was not an act of luck, nor solely of courage, but of deliberate design. That insight reshaped the course of military aviation, from the piston age to the nuclear era. When the last active-duty B-17s were retired in the 1950s, many were scrapped quietly, their metal melted down for post-war reconstruction. But a few survived: museum pieces, gate guards, film props, and airworthy veterans. Standing beneath one today, you can still see the riveted seams where armor meets structure, the redundant cable housings, the fuel isolation valves, all silent witnesses to an idea that changed everything. That idea was never about making the aircraft indestructible. It was about making it endure, to take damage and keep flying, to protect its crew not with luck, but with logic. The engineer's weird modification didn't make the B-17 truly untouchable, but it made it something more meaningful. It made it human-proof. It made it forgiving. It turned a machine of war into a triumph of reason over chaos. In a conflict defined by destruction, that small act of creation, a smarter way to build, a wiser way to fail, became one of World War II's quietest and most enduring victories. If you enjoyed this video, don't forget to like, comment, and subscribe for more World War II stories.